So continuing our lesson, let's not talk about the history of the atomic theory, and that will set the stage for us for looking at the modern description of what an atom is. Okay, so let's talk about the concept of atomism first. The idea that things are made up of atoms started off as a philosophical idea. It has no basis in fact. Okay, so it's just an idea, and that idea is known as atomism. The basic idea was that if you can imagine, you can always divide matter into smaller pieces, right? And if you can keep dividing a smaller piece into even smaller pieces, the rationale was, okay, Democritus proposed that eventually you'll get to a point that you can no longer separate that last bit, that small bit of matter. So once you get to the point where you have the smallest possible bit of matter, Democritus said what you have there is called an atomos. Okay, A in Greek is a prefix, which means not. Tomos is cut. So atomos means cannot be cut. Okay, so the philosophy of atomism basically says that ultimately, once you cut everything up into little pieces, you get to a point where you can't cut it anymore into even smaller pieces. And so that smallest possible bit of matter that you have is called the atom. So they postulated then, they assumed that the universe is made up of atoms and the void. Everything else in between those atoms, there's just nothing there. Okay? So, unfortunately, there was no supporting evidence for this idea. Okay, Greek philosophers were more thinkers than workers, so they didn't really have any experiment. They didn't really do any experiments that would validate their idea. So the idea of atomism did not flourish until much later. And one of the reasons it didn't flourish was that it's really contrary to the beliefs of the more influential people. Okay, which would be like the Greek philosophers Plato and Aristotle. And the idea was even something that wasn't approved by the church, because it sort of made people, if we people are made up of the same things as everything else in the universe, so it doesn't make us special. Okay, so that was a problem with atomism. It took a while for the idea to be accepted. Okay, somewhere between the acceptance of the concept of atoms and the time it was proposed by Democritus, a field known as alchemy, okay, was developed, and this sort of serves as a bridge between the Greek philosophers' pure thought and what we now call as modern science. So alchemists, the major contribution of alchemists is in the development of laboratory techniques that would eventually be used for scientific work, because they try to do a lot of work in the lab. And their goals, okay, here's some of their goals of alchemists. One is to convert metals into gold or silver, and that process is known as transmutation. Okay, to cure diseases using herbs. Okay, to create an elixir of life. Okay, a panacea. And to create a universal solvent, also known as an alkahest, that can dissolve anything, which was sort of, for lack of a better word, somewhat stupid, because if you have a solvent that can dissolve anything, how can you contain it into? It will also dissolve whatever container you put it in. So, but anyway, alchemists tried to do these things, and in the process of trying to accomplish these goals, they were able to develop a lot of nice laboratory techniques that were eventually used by chemists. Okay, now so the idea of atoms, okay, was elevated to a scientific theory by John Dalton. Okay, and based on his numerous experimental data, not just those he got, but those by other scientists at the time, he was able to summarize, okay, all the experimental data that were known at the time by making just a few assumptions. So these are the assumptions that he made, or postulates, that allowed him to explain the behavior of matter. And so let's take a look at these postulates that Dalton made. First of all, he said that matter is made up of indivisible particles called atoms. So that was the major assumption. So that's why it's called the atomic theory. usually when a theory is, the name that you give to a theory is based on what is the most important major assumption that you're making. And so the most important major assumption that Dalton was making is that matter is ultimately made up of indivisible particles called atoms. Okay. He also assumed that all atoms of an element have the same mass. So the only way atoms differ from each other, according to Dalton, is by mass. So if you have atoms that have the same mass, they're atoms of the same element. Okay, so that's what makes one element different from another. They have different atoms with different masses. Of course, we now know that this isn't true anymore. Okay, so that's one thing you realize about theories in science is they evolve as you uncover new information. You make changes in your assumptions. So what we now have is no longer the theory that Dalton proposed. It's a revision of Dalton's atomic theory. We now know that atoms of the same element, they don't have the same mass, but they have the same number of protons in the nucleus. But they didn't know that at the time. So as far as experimental information at the time was concerned, postulate number 2 here was good enough. Okay, so all atoms of an element have the same mass. He also said that if you have different elements, then they have different atoms. The atoms of different elements would have different masses. Okay, and he was able to explain the law of definite composition. Okay, he said that in compounds are substances that have definite composition. The atoms of the different elements are combined in a fixed whole number ratio. Okay, so that led to the notion of a formula for a compound. So if you were to write something like H2O for water, that's saying that in a compound of water, you can explain why it has a definite composition by saying that for every oxygen you find in that compound, you're going to find 2 hydrogen atoms. And then postulate 5 of Dalton, okay, assumes that when we observe changes around us, when changes occur, physical change, chemical change, the atoms are neither created nor destroyed. They simply rearrange. Okay, so those are Dalton's original assumptions. And as we can see, which of these postulates are no longer valid? We said that postulate number 2, well, postulate number 1 we now know is no longer valid. Okay, what's the modern interpretation of atoms? What Dalton called atoms, eventually we figured out based on later experiments that those things that Dalton called atoms are actually made up of even smaller particles, subatomic particles, the protons and neutrons and electrons, right? Postulate number 2, all atoms of the same element have the same mass. That's no longer true. We've learned about isotopes, right? So they can have different masses. They just have to have the same number of protons. Postulate number 3, same thing. You can have isotopes of different elements can have similar masses. Okay, essentially the same mass. All right. Number 4 is still okay. Okay, compounds. The atoms of different elements are combined in a fixed whole number ratio in a compound. And number 5 is pretty much okay except that if you think of just losing and gaining electrons as not destroying the atom. What really happens in chemical change is the nuclei remain intact. But even that is no longer true because the nucleus, we do know you can have some unstable nuclei, radioactive nuclei. So postulate number 5 is also false. This is generally true for chemical and physical changes. And for chemical changes, it's true if you don't consider the gaining or losing of electrons as destroying the atom. Okay? All right. So what are some of these experiments that Dalton based his theory on? One series of experiments was done by Antoine Lavoisier, who's known as the father of modern chemistry. He was the one who formulated what's known as the law of conservation of mass or matter. So Antoine Lavoisier, based on numerous experiments that he did, those experiments led him to the conclusion that matter is neither created nor destroyed. So in 1780, he did a series of experiments involving hydrogen and oxygen. He put them in an enclosed chamber and introduced an electrical spark. He got water. He measured the mass before and after the reaction, found that they're the same. So that led to all of these experiments that Lavoisier did eventually led to the notion that generalization that matter is conserved. Matter is neither created nor destroyed. So a law, when we talk about a law in science, we're talking about a generalization, a general observation. Okay? So how does Dalton explain the law of conservation of mass? Dalton says you can explain that by saying that matter is made up of atoms. If you cannot destroy atoms, then you cannot create or destroy mass. Okay, so that's a simple explanation for the law of conservation of mass. All right. Now, how do we explain the law of conservation of mass these days? Well, pretty much we can say that for most of the changes we observe around us, okay, mass is still conserved. It's not, strictly speaking, it's not really true anymore. It's really conservation of mass within our ability to measure mass in most cases. But if mass is not really conserved, because we now know mass can be converted into energy, Einstein's equation E equals mc squared. But the amount of energies involved in the typical changes that we observe around us would involve changes in mass that are typically imperceptible to us. Okay, so beyond our ability to measure mass, at least in typical everyday situations. Okay, so that's still pretty much a valid assumption in most cases. Okay. The law of definite composition was formulated by Joseph Proust based on a series of experiments he did in 1797 to 1804. Okay, and if you recall, that law says that when a substance that is made up of two or more elements, which we call a compound, is broken down, the mass ratio of the components, the elements, would always be the same. Okay, so we say it has a definite composition. So when you form a compound from the same elements, you always need the same proportion of elements to make the compound, and you break it down, the proportion of the elements is always the same. Dalton's explanation for that is to say that compounds have a formulas. So the number of atoms of different elements that are combined in a compound are in a fixed whole number ratio. Okay, so let's look at an example of how you might explain a definite composition using Dalton's assumption. Okay, so let's say that the atom count ratio for X and Y is 1:2. Okay, that means there's 2 atoms of Y for every atom of X. Okay, one atom of X. Every time you see 1 atom of X, you're going to see 2 atoms of Y. So that's the count-to-count ratio, 1:2. So let's say you have a sample and you have n X atoms. Okay, then the number of Y atoms would be how much? If I have 5 X atoms, I have 10 Y atoms. I have 7 X atoms, I would have 14 Y atoms. So if I have n X atoms, the number of Y atoms would be 2n, right? Now let's say the mass of each single atom of X is little x right here. So the total mass of the X atoms would be 2n, it would be n times x, right? There's n X atoms, each one has a mass of x, okay? So number of atoms times the mass of each atom gives you the total mass of X atoms. Similarly, then you would say if little y here is the mass of one atom of Y, then the total mass of the Y atoms in that sample would be the number of Y atoms, which is 2n, multiplied by the mass of each atom, which is Y. Okay? Let me rewrite this. 2n times Y. So what's the ratio of the mass of X atoms to the mass of Y atoms? It's just going to be nx divided by 2ny. But if you did this, your n cancels out, so that just gives you x over 2y. Well, x is the mass of an atom of x, so that's a constant. Little y here is the mass of an atom of y, so that's also a constant. So this is a constant, that's a constant. The number 2 is a constant. A constant divided by a constant times a constant is just a constant. So that explains why the mass-to-mass ratio is a constant. Okay, so by assuming that the compound has a definite formula which reflects the count-to-count ratio of atoms, you can explain why the mass-to-mass ratio is constant. You can also explain why the percentage, okay, or the fraction of the mass due to each element is a constant, because what's the mass of x related to the total mass? Mass of x is nx. The total mass is nx plus 2ny, right? And if you did that, you can factor out n from the bottom. You can say n times x plus 2y, and n cancels out. That gives you x over x plus 2y. Everything here is a constant, so that mass, the ratio of the mass to the total mass, that's called the mass fraction, is also a constant. Okay, so that explains the law of definite composition. So that's how you explain the law of definite composition if you were to assume that the count-to-count ratio of the different atoms is a fixed number in your compound. All right. The law of multiple proportion was also formulated by Dalton based on experiments he did, and the law of multiple proportion basically says that if you have, let's say you have two different compounds, okay, and they're made up of the same two elements, but they're different compounds, then Dalton said that if the experimental observation suggests that the ratio of the mass ratios of the two elements, okay, you take the mass ratio of two elements in one compound, you take the ratio of those two elements in another compound, the ratio of the two ratios can be reduced to a small whole number ratio. For example, let's say I have one compound here. We can use a modern example here. Let's say methane, okay? The mass-to-mass ratio of carbon to hydrogen in methane. Let's say you have a sample of methane. You broke it down into carbon and hydrogen, okay? So you weigh how much carbon you get from the sample of methane. You weigh the hydrogen that you got from your sample of methane. You'll find that mass-to-mass ratio is 2.979. You can experimentally determine that. Mass of carbon over mass of hydrogen. Okay, carbon to hydrogen ratio in methane, mass to mass is 2.979. You can weigh that in the lab. Okay. If you have another compound that's also made up of carbon and hydrogen, and that compound, let's say, is ethylene or ethene, okay, and you were to go to the lab and figure out the carbon to hydrogen mass ratio, you'll find that it's 5.958. So I have a ratio of carbon to hydrogen in methane, a ratio of carbon to hydrogen in ethene. The ratio of these two ratios, so 2.979 over 5.958, this ratio of ratio, okay, you can reduce that to a whole number ratio. That's just equivalent to 1 over 2. It's 1/2. Or you can say 5.958 over 2.979 is equal to 2. So 2 is a ratio of two whole numbers. 2 is to 1. So that is the law of multiple proportion. So how does Dalton explain the law of multiple proportion? Let's just look at it from a modern day explanation. You can just say, okay, carbon to methane is CH4, okay? Carbon to hydrogen in methane is 1:4. So this is the modern explanation for this. Methane has a formula of CH4, and ethene has a formula of C2H6. Yeah, ethene C2H4, I'm sorry. Okay, so this is ethylene or ethene. Okay, well, what's the carbon to hydrogen ratio in methane? Carbon is 12.01. Hydrogen, you have 4 hydrogens, so that's over 4 times 1.008, right? That's the carbon to hydrogen ratio in methane. What's the carbon to hydrogen ratio in ethane? C2H4. The ratio would be 2 times 12.01 divided by 4 times 1.008. Okay? So this is the ratio in C2H4, C2H ratio. So this one on top here is for methane. The one at the bottom is for ethylene, C2H4. Well, what do we get here? If you take the ratio of these two ratios, you get 12.01 cancels out, 1.008 cancels out, 4 cancels out. You just get a ratio of 1:2. Okay? By assuming that methane and ethylene have formulas of CH4 and C2H4, then you can show that the ratio of mass ratios of carbon to hydrogen is going to be a small whole number ratio. So that would explain the law of multiple proportion. Okay? And that's what we did here. Okay? So we now know that methane is CH4 and ethane is C2H4. So carbon to hydrogen, so C here is 12.01. Modern value for mass of carbon atom is 12.01. The mass of a hydrogen atom is 1.008, right? So mass of carbon divided by 4 times the mass of hydrogen atoms, okay, would be the mass to mass ratio in CH4. The carbon to hydrogen mass ratio in C2H4 would be 2 times the mass of each carbon atom divided by 4 times the mass of each hydrogen. So if you take the ratio of mass ratio, C over 4H over 2C over 4H, H cancels out, 4 cancels out, C cancels out, that gives you 1:2. Okay? So that's how you can explain the law of multiple proportion by assuming that compounds have a well-defined formula. Okay, so let's take a look at this example. Compound of elements X and Y, so it's made up of X and Y, is found to be 85.71% X by mass. According to the law of multiple proportion, which of the following mass percent of X is more plausible for another compound of X and Y? Well, if you have another compound of X and Y, then the X to Y ratio in our given compound, right, divided by the X to Y ratio in your other compound must be a small whole number ratio. Okay? So the question is, you need to get that ratio of ratios. So to solve this problem, you say, all right, let's figure out the X to Y ratio in the given compound. So in the given compound, X to Y ratio is how much? 85.71% X, right? So if I have 85.71 grams of X, how many grams of Y would I have? Let's say a compound is 85.71% X. How much Y would I have in the compound? (14.29). Good. So the mass to mass ratio in the given compound is how much? Let's see. Calculator. 85.71 divided by 14.29. That's 5.998. Okay? Now, let's look at the other compound. Let's pretend A, what if A was the correct answer? Okay? So if A is another compound of X and Y, What would be the mass to mass ratio in compound A? If it's 80% X, so it's going to be 80 grams X. Yes, 80 to 20, very good. So it's 80 grams X to 20 grams Y. The mass ratio is 8:2, or that's going to be 4, right? 4.000. What would that ratio be for the other compound? If B was another compound of X and Y, what would be your X to Y ratio? So according to this, B is 84.32% X. 84.32 grams X. How much Y would that be? Okay, so 100 minus 84.32, that's 15.68. Grams cancel out. What would that be? $84.32 divided by 15.68. That's 5.378. Okay, let's just eyeball this. Can you reduce this ratio into a whole number ratio? A ratio of two small whole numbers. This is almost a 6, right? So that's a 6:4, or 3:2. So it's possible that A is another compound of X and Y. Okay? But what about 5.998 and 5.738? You cannot reduce that to a ratio of two small whole numbers. And in fact, what's the ratio of 5.998 to 5.378? So let's take 5.998 divided by 5.378. What would that be? That's going to be 5.998 divided by 5.378. That's 1.115. Okay? So that's like 1115 to 1. That's a big ratio. Okay, so it's very unlikely then that B is another compound of X and Y. Okay? So if you have two compounds of the same two elements, two different compounds, the ratio of their mass ratios must be a small whole number ratio. So the correct answer here would be A. Okay? So you look at the ratio of ratios. So how can you tell that you can reduce a number into a small whole number ratio? Well, first of all, if it's already a whole number, so you divide one by the other, you get the whole number, then you have a small whole number ratio. Like 3 is a ratio of 3:1, right? Now, if you get a decimal, then all you have to do is multiply it by 2/2, 3/3, 4/4, until you get your numerator as close as possible to a whole number. So let's take a look at this 1.199. Okay, is that a ratio of two small whole numbers? Well, you start by multiplying that by 2/2. So 1.199 times 2 is 2.398. That's far from a whole number. Okay, so that doesn't work. Multiply it by 3/3. What's 1.199 times 3? That's 3.597:2. That's still far from a whole number. 3.597 is far from a whole number. Okay, what about 1.199 times 4? That's 4.9796. So 4.796/4. 4.796 is still too far from a whole number. So that's not going to work. How about 5? You try 1.199 times 5, that gives you 5.995 is to 5. Now that is very close to a whole number. So you can say that this is essentially equal to 6 is to 5, 6 over 5. So that ratio, 1.199, is a 6 is to 5 ratio. Okay. In fact, if you divide 6 by 5, what do you get? You get 1.2, which is really what 1.199 is essentially. Okay, so if you wanted to say, if you want to know whether a ratio of two numbers can be written as a small whole number ratio to within experimental uncertainty, then you just do this procedure right here. Divide the bigger one by the smaller one. If you get a whole number, then that's a ratio of small whole numbers. Otherwise, multiply it by 2 over 2, 3 over 3, 4 over 4, until you get a small whole number ratio. And the numerator becomes a number very close to a whole number. If it doesn't happen, after a while, then you just say it has to be a big ratio. Okay, it's not a small whole number ratio. All right, let's just do a quick check of Dalton's theory. Which of the changes indicated below is possible, A, B, or C? According to Dalton's theory, okay, correct answer is C. Okay, what's wrong with A? You lost an atom, right? You lost an atom. What's wrong with B? You made an extra atom. Okay, and C, the only thing that happened in C was the atoms rearranged. Okay, and so that's what we talked about that earlier this semester. That's what we said, that was a chemical change, right? How about this one? Assume circles and squares in the figures below represent different kinds of atoms. A circle will be a different kind of atom from a square. According to Dalton's atomic theory, which of the figures best represents a sample of a compound? All right, very good. This one is a compound, okay? This is a pure element, okay, and that's a pure element. An example of this would be O2, right? An example of this would be something like helium, okay? This is a mixture of two elements. And this one is a compound. Good. That's pretty straightforward. Okay. How about this one? Using the pictorial representation below for the molecular composition of a mixture, using Dalton's atomic theory, the figure represents a mixture of an element and two compounds, two elements and a compound, three compounds. All right, so here you have, okay, this would be same elements, right? For both atoms. So that's an element. And this would be also another element. Okay. And then this would be right here, a compound. So that's two elements and a compound. All right? Very good. Is it almost time to quit? Let's try this one. The mass of atom X is 10 times the mass of atom Y. Dalton explained that an observed X to Y ratio of 5:1 in a compound means that the X to Y atom count in the formula is 1:1, 1:2, 2:1, or 2:3. In other words, what this is saying is that the formula of the compound, is it XY, is it XY2, is it X2Y, or is it X2Y3? What's the formula of the compound? If the mass of X to mass of Y ratio is 5:1. And you are told that an atom of X is 10 times, oops, what did I just do? Okay. An atom of X is 10 times more massive than an atom of Y. How would you work this out? Let's say the molar mass of X is 10, okay, and the molar mass of Y is 1. Doesn't really matter since it's all about proportions, okay? So what if the mass ratio is 5:1, okay? Is the formula XY? Is it XY2? Is it X2Y? Or is it X2Y3? Most said C, 2:1. Let's see. If it is C, okay, what would be the mass of X? Let's say you have two atoms of X, right? Mass of two atoms of X. How would that compare to the mass of one atom of Y? Okay. Then what would that be? According to this, it's going to be 5:1, right? Would that be consistent? So let's call this it's 2 times 1 over 1 times, what's the mass of atom X? It's 10, right? So it's 2 times 10 over 1 times 1. Is that equal to 5:1? Would that be correct? Remember, X is 10 times more massive than Y, right? So mass of X over mass of, if so, mass of X is 10, the mass of Y is going to be 1. So 2:1 is not going to be correct because mass of two atoms of X would be 20 times heavier than mass of one atom of Y. So it's not C. So what is it? Okay. So it's not C. What's the other possibility? B? Okay. What if it's B? Then you say mass of 1x over mass of 2y's. Is that equal to 5:1? Well, what's 1x? Remember, x is 10, right? And y is 1, so 2y's. Is that equal to 5:1? And the answer would be yes. So the correct answer here is we say that the formula of this compound is XY2. The count-to-count ratio of X atoms to Y atoms is 1:2. Okay? I think this is a good time to stop.